Welcome to How the Heavens Go. I'm your host, Mark Lesmeister. In our last episode, we looked at the reaction to the publication of the Copernican model of planetary motion. The realization that the Earth was not at the center of the cosmos, but was, in fact, one of several planets orbiting the Sun, seems to us to have been a demotion, but it wasn't necessarily viewed that way by the people at the time. Historically, being at the center of creation was often seen as a bad thing. In the Middle Ages, the center of the cosmos was often portrayed as the home of some frightful beast, or, as in Dante's Inferno, Satan. Galileo in particular wanted to show the Earth was not at the center, which he described as the, quote, sump where the universe's filth and ephemera collect. Whether Copernicus's model represented a promotion or a demotion for the Earth, the fact is the model had some problems that needed to be addressed. One of those who attempted to do that was the Danish astronomer Tycho Brahe, often known as Tycho. Tycho was born in 1546, just a scant 3 years after the publication of Copernicus's On the Revolutions. He studied law and other typical subjects of the day, but became interested in astronomy, particularly after observing an eclipse in 1560 that had been predicted far in advance. At the age of 20, while studying medicine at the University of Rostock, he got into a feud with a distant cousin over who was the better mathematician. This would eventually lead to a duel which cost Tycho part of his nose. Tycho was a member of the nobility, but he had little interest in the affairs of state. He preferred to devote his time and resources to his primary passion, astronomy. With the help of various benefactors and his own considerable wealth, Tycho built a succession of ever more elaborate observatories to carry on his research. At one of these observatories in November of 1572, he observed a bright new object in the sky. Through a series of observations over the next few months, he concluded that it was not a new planet, but a new fixed star. This finding was very significant because it challenged the immutability of the heavens. His book describing his findings, De Stella Nova, or On the New Star, is where we get the word nova. In 1576, with the support of King Frederick II of Denmark, he started construction of the Uraniborg Observatory on the island of Hven. In 1577, he made observations of a new comet. These observations convinced him that comets were not atmospheric phenomena as was commonly believed. Moreover, they traveled across the orbits of the planets, throwing doubt on the idea that the planets were attached to transparent spheres. In the 1580s, he was one of the richest men in Denmark. Uraniborg became a research center which hosted numerous students and artisans. He gave lavish dinners. His entourage included a tame elk. Tycho developed a hybrid theory of the cosmos in which the sun and the moon orbited the Earth and everything else orbited the sun. In its simplest form, this idea mathematically would be identical to the Copernican model. After all, in the Earth's frame of reference, it is at rest. If I were to hold the Earth here still on this model, and then have somebody turn the crank, and I can't do it on this model because it's not that robust, but the whole model would then rotate around what appears to be the stationary Earth. And I could have the other things that are involved in the Copernican model, such as Venus with its phases, and that would still be represented here because the motion is the same regardless of which thing we're saying is standing still. In 1597, Tycho left Uraniborg, and in 1599 he became the imperial mathematician to the Holy Roman Emperor Rudolf II. There he would continue his astronomy research until his death in 1601 due to a bladder or kidney ailment. There are some legends and even a conspiracy theory or two surrounding Tycho's death, but I prefer to focus on his contributions to astronomy. Tycho's greatest contribution to astronomy was his extensive collection of extremely accurate and precise observations. Many of these were made with the sighting devices he designed himself. He is generally considered to be the greatest observational astronomer of the pre-telescopic era. In the last year of his life, Tycho was assisted by an astronomer named Johannes Kepler. Kepler was born in the German town of Walderstadt in 1571. Like Tycho, Kepler's early experiences with astronomy, including viewing the comet in 1577 that Tycho wrote about, led to a lifelong interest in the subject. However, damaged vision resulting from a childhood bout of smallpox meant that he was not destined to be a great observational astronomer in the matter of Tycho. Kepler came to Prague to work as Tycho's assistant in 1600, temporarily at first as Tycho's guest, and then full-time. Tycho set Kepler to work analyzing the orbits of planets, in particular Mars. When Tycho died suddenly in 1601, Kepler was named the new imperial mathematician. He also took possession of Tycho's copious data. Over the course of the next few decades, Kepler would make numerous contributions to science. He is best known for his 3 laws of planetary motion. The first of these laws to be discovered is known for historical reasons as Kepler's second law. It deals with 2 problems that had vexed astronomers. One was that even in the heliocentric system, the planets didn't orbit around the Sun, but a point near the Sun. This meant that a planet would move closer to and farther away from the Sun as it orbits. The most distant point from the Sun in the orbit is called the aphelion, and the closest point is called the perihelion. The second problem was that the planets didn't move at constant speeds. If the solar system was a giant Lego model, someone was turning the crank faster or slower, and every planet had a different crank. Kepler essentially turned these bugs into a feature. Using data from the observations of Mars and the Earth, Kepler saw that the farther a planet was from the Sun, the slower it moved. He reasoned that it might be because the Sun was causing the motion in some way, and that influence decreased as the distance from the Sun increased. His willingness to go beyond simply describing motion and actually try to explain it was significant. Now, his concept of force produced by the Sun was mistaken, and his derivation of what we now call his second law was incorrect, but the principle he discovered has held up. Kepler would eventually express the change in speed in terms of the area swept out by a line joining the planet to the Sun. The idea is this. If we draw an imaginary line from the Sun to the planet at some point in the orbit, and then after a certain amount of time, say 1 month, draw a second line, and then repeat this process at a different part of the orbit, we will find that the areas defined by the orbit and the 2 imaginary lines at every part of the orbit are equal. In this example, the slow-moving planet at aphelion has a shorter arc but longer lines than the fast-moving planet at perihelion. We now know that the second law can be explained using a principle called the conservation of angular momentum. We see this principle in action when a figure skater spins rapidly when her hands are held close to her body, but slows down when her arms are outstretched. Kepler's second law wasn't of much practical use in his time. Areas would be difficult to measure precisely, but it did lead Kepler to discover another principle of planetary motion. In deriving his principle of equal areas, Kepler had assumed, like everyone else before him, that the planets moved in circular paths. However, he soon realized that while the principle worked well enough to describe the motion of Mars near perihelion and aphelion, the principle didn't really work for all parts of Mars' orbit if that orbit was circular. So then he tried using other shapes for the orbit to see which best fit Tycho's data. One method Kepler used to test various shapes was a triangulation technique involving pairs of observations of Mars that were made 1 Martian year apart. Here's a diagram I made using the technique with some actual Mars data. The circle represents the orbit of the Earth. We first plot the position of the Earth at the time of the observation, and then draw a line showing the direction to Mars on that day from Earth. We do the same thing for the data from 1 Martian year later, when Mars should be at the same point in its orbit. The intersection of the pairs of lines are meant to show points on the Martian orbit. Kepler describes this technique, but likely only used it as a general guide, since it doesn't allow for the kind of precision he needed. Here's my crude guess at the orbit of Mars on my model. The shape Kepler came up with was the ellipse. The Sun is not at the center of the ellipse, but at one focus. Kepler's willingness to move beyond circular motion, a feature of every planetary system before him, was a major milestone. Gone was the need to include epicycles and eccentrics to explain variations in the distance to the planet from the Sun. In its place was a well-known geometric shape with a built-in variation of the distance to the sun. Kepler believed strongly that there was order in creation, and that to study that order was to study the mind of the Creator. Even before he came to work for Tycho, he searched for that order in the relative sizes of the planetary orbits. Kepler had a hypothesis about this based on the shapes known as the Platonic solids. The theory never really worked, but it showed how he was willing to use intuition and models brought from other areas of math in order to come up with a theory for planetary motion. Later on in his career, he would look for order in the speeds of the planets, specifically the ratio of the speed of the planet when it was closest to the sun and moving its fastest to the speed when it was farthest away and moving slowest. He compared these ratios to the ratios of musical frequencies that formed harmonies when played together, even coming up with scales for the various planets. The idea that the mathematics of celestial motion was analogous to music, a concept known as music of the spheres, had been around since antiquity. He described this research in a book he titled Harmonices Mundi, which means harmonies of the world. However, it isn't his musical ideas that are of interest to us for this video. In the course of this research, Kepler discovered the important relationship known as his third law of planetary motion. The period is the time it takes for the planet to go around the sun once. That is, it is the length of the year for that planet. The major axis is the long axis of the ellipse of the orbit, shown in red here. The semi-major axis is half of that line. We sometimes call the semi-major axis the radius of the orbit, since if the orbit is circular, the radius is equal to the semi-major axis. Most of the planets have fairly circular orbits. Kepler's third law says that if one squares the period of a planet and divides the result by the third power of the length of the semi-major axis, the answer will be the same for all the planets. On the following graphs, each planet is represented by a dot. The vertical coordinate of each dot represents the period of the planet squared, and the horizontal coordinate represents the radius of the orbit cubed. According to Kepler's third law, the dots should all lie on the same line. Because the distance scales for the inner and outer planets are so different, I had to draw different graphs. The first graph shows the inner planets. The second shows the outer planets, two of which were unknown in Kepler's time. The third shows the dwarf planets, all of which were unknown in Kepler's time, including Ceres, which is one of the asteroids orbiting the Sun in the asteroid belt between the orbits of Mars and Jupiter. The fact that they all fall on a straight line indicates Kepler's third law holds for all of them. Kepler determined that his third law even could be applied to the 4 moons of Jupiter that Galileo had recently discovered. The ratio of the period squared to radius cubed for the Galilean moons would be the same for each of the moons, though it would differ from the ratio found for the planetary system. I don't want to give a Facebook view of Kepler's life, i.e. one where I only show you the positive things that happened. Kepler lived at a time of political and religious upheaval in Europe, in the years before the 30 Years' War. Kepler had to move out of Catholic Inner Austria when policies allowing Lutherans to live there were rescinded. He also faced discrimination from Protestant authorities because of his unorthodox religious beliefs. He even had to interrupt his research for months to help defend his mother, who was a healer and herbalist, against charges of witchcraft. But through it all, he persisted. Kepler's search for order in the planetary system, aided greatly by Tycho's observations, would bear fruit about a half a century later. Isaac Newton would use Kepler's laws of planetary motion as evidence for his law of gravity. But that's getting into why the heavens go. And we're still talking about how the heavens go using our model, because there's one more part we haven't discussed yet, namely the moon. So we will talk about that next time. Until then, look to the stars.